We will continue solving examples about statically determinate plane trusses using the method of section. So here is our next example. The requirement of this truss is to solve for member force DG, DE, HE, and BF. We have some simple steps to follow in order to solve for the problem. The first step is to check the determinacy of the truss. The second step is to solve the support reactions. The third step is to pass cutting plane that will cut the portion of truss where member force are desired. Then for the fourth step, we will replace the severed members with the force, and for the fifth step is to apply equations of static equilibrium in order to solve the unknown member forces. We will now proceed to step 1. We check the determinacy of the truss. We will count the number of members, joints, and support reactions components. For number of members, that is equal to 13, and for joints, that is equal to 8. For support reactions, we know that for a roller support, we have 1 component, and for a hinge support, we have 2 components, horizontal and vertical components. So here is a hinge support. We will now substitute the value of M and R into our equation, that is M plus R. So that is equal to 16, and for twice of J, that is also equal to 16. If M plus R is equal to twice of J, that is 16 is equal to 16, the truss is statically determinate and externally stable. If the truss will be externally unstable, there is no need to continue the calculation. We will only continue the calculation if that is statically determinate and externally stable. We can be able to solve all the member forces of this truss together with the support reactions using equations of static equilibrium. But if the truss is statically indeterminate, we can proceed to the calculation after studying about truss deflections, because equations of static equilibrium will no longer enough to solve for the problem. We will now solve for the support reactions. We will label the direction of support reactions. All those directions are assumptions, but if we can investigate the truss and label the correct directions of forces, then we can make the calculation more simple or straightforward. Just like the horizontal reaction at point C, we know that 50 kN and 25 kN applied at point G and D of the truss is acting to the right. So therefore, the reaction at point C should be a leftward support reaction to counteract the two forces 50 kN and 25 kN acting to the right. We will now apply summation forces along X is equal to 0, rightward forces positive. Since 25 and 50 kN are rightward forces and Cx is leftward, we have positive 50 and 25 and Cx that is negative on the equation. So from this equation, we can be able to solve for the value of Cx that is equal to 75 kN. Since 75 came out to be positive, then our assumption that Cx is acting to the left was correct. After solving for Cx, we will apply summation moment at A. We consider clockwise moment are positive. So this is our moment center at point A. We have 25 multiplied by its moment arm, that is 5 meters, and 50 multiplied by its moment arm, 10 meters, are clockwise moment with respect to point A. Cx will not create moment with respect to point A because it will pass through the moment center. Cy multiplied by its moment arm, that is 8 meters, is counterclockwise with respect to point A. We can now observe that 50 times 10, that is clockwise positive, 25 times 5 clockwise positive, Cy times 8, that is counterclockwise, therefore that is negative. From that equation, we can solve for Cy, and that is equal to 78.1 kN. Since 78.1 came out to be positive, our assumption that Cy is an upward support reaction was correct. After solving for support reaction at point C, Cx, and Cy, we will apply summation moment at point C to solve for support reaction at point A, that is Ay. We have 25 multiplied by 5 is clockwise with respect to point C. 50 multiplied by its moment arm 10 meters is clockwise also with respect to point C. And Ay multiplied by 8 meters, that is the moment arm, is still a clockwise moment with respect to point C. So we can observe from applying summation moment at point C is equal to 0, we have 3 terms of the equation, all are positive because those are all clockwise moment with respect to point C. So from this equation, the only unknown is Ay, that is equal to negative 78.1 kN. Our assumption that Ay is upward was incorrect, that is a downward reaction, since 78.1 came out to be negative, our assumed direction was incorrect. We can now apply summation forces along vertical to verify if our answer was correct. So we will replace the value of Cy, that is an upward reaction at point C, and Ay, that is a downward reaction at point A. 78.125 minus 78.125 is equal to 0. Therefore, 0 is equal to 0. We satisfy equation of static equilibrium summation forces along vertical. The values that we have solved for the support reactions are correct. We will now proceed to step number 3 to solve for member force GD, DE, HE, and BF of this truss. We have to pass cutting plane that will cut those member forces. Like for example, if we pass cutting plane B dash B, we can observe that we have left with 4 unknowns, that is HF, HE, GE, and DG. We have only 3 equations of static equilibrium, therefore we can solve all those member forces using the free body diagram above the cutting plane or below the cutting plane. We should understand that some of the member forces cannot be obtained directly on such cases. We should solve first the adjacent member forces before we can solve for the unknown member forces. For this kind of problems, the technique is to pass another cutting plane. So here's the cutting plane, wherein we can make use the upper portion of this cutting plane as free body diagram, and if we apply summation moment at joint D or joint F, 3 member forces which are unknown will intersect at those joints. So like for example, at joint D, we have DG, DE, and EF. Those will intersect at the moment center at joint D, thereby the only unknown will be member force HF. And if we apply summation moment at F, DE, EF, and HF will intersect at our moment center, that is joint F. The only unknown will be member force DG. So after solving for member force HF, we can be able to pass this cutting plane. We can use the free body diagram above this cutting plane. Then we can observe that we have 3 remaining unknown member forces, that is HE, GE, and DG. Therefore, using 3 equations of static equilibrium, summation forces along X is equal to 0, summation forces along Y is equal to 0, and summation moment, we can be able to solve for those member forces. We will now pass cutting plane A dash A, then we will select the upper portion as our free body diagram. So here is now our free body diagram. We replace the severed member with the force, and all the direction of those forces are assumption. After we solve or perform the operation and the value came out to be negative, then our assumed direction was incorrect. We can now apply summation moment at joint F in order to solve for member force DG, because we know that DE, EF, and FH will pass through our moment center at F, and they will not create moment with respect to point F. Assuming that clockwise moment are positive, summation moment at F is equal to 0. We have 50 multiplied by its moment arm, that is clockwise moment with respect to F. Then we have DG multiplied by its moment arm, that is 8 meters, that is a counterclockwise with respect to joint F. So 50 times 5 is positive, and DG times 8 is negative in our equation. So from this equation, we can solve for member force DG, that is equal to 31.25 kN. Our assumption that DG is acting away the free body diagram was correct, that is a tensile force. So I write here that is tension. After solving for member force DG, we can apply summation moment at point D in order to solve for member force FH. Assuming that clockwise moment are positive, summation moment at D is equal to 0. We have 50 multiplied by 5 is clockwise moment with respect to joint D. Then FH multiplied by 8 meters is a counterclockwise moment with respect to joint D. Therefore, we can solve for FH, and that is also equal to 31.25 kN. And our assumption that FH is acting toward the free body diagram, that is compression, was correct. After solving for member force FH and DG, we can now pass this cutting plane, that is cutting plane B dash B. We will again replace the severed member with forces, and we assume direction of those forces. After we solve, the result is negative, then our assumption was incorrect. Those forces should act opposite to our assumed direction. But since GE and HE are inclined member forces, we have to resolve its vertical and horizontal component to this reference triangle. The vertical component of HE, that is HEY, is equal to the vertical dimension divided by the hypotenuse of triangle, that is equal to 5 divided by square root of 4 square plus 5 square, or 5 divided by square root of 41. If we perform the operation, that is equal to 0.781 of HE. And since HE and GE have the same inclination, the vertical component of GE is also equal to 0.781 of GE. And for the horizontal component, that is equal to the horizontal dimension divided by the hypotenuse of the triangle, that is equal to 1.5 divided by square root of 41, is equal to 0.625 of HE, and that is also equal to 0.625 of GE for the horizontal component of GE. So 4 and 5 dimensions are given from the truss dimensions. So we know that this is equal to 5 meters, and horizontal is equal to 8 meters divided by 2, that is equal to 4 meters. We will now apply summation moment at any point on our free body diagram. Our mindset is to find a joint wherein some of the forces will intersect, to eliminate them from the equation. In our case, we can select joint G as our moment center, where DG, GE, and 50 kN will intersect. So thereby, we can have only two forces that will create moment with respect to joint G, and that is only HE and FH. Since FH was already solved from our previous calculation, the only unknown now will be HE if we apply summation moment at G. But HE is an inclined member force, so therefore we have to resolve HE anywhere to its line of action by applying the principle of transmissibility. It is now logical to resolve HE at joint H such that the horizontal component of HE will pass through the moment center, thus it will not create moment, and only the vertical component will create moment with respect to joint G. Of course, we can obtain the same result if we resolve HE at joint E, vertical and horizontal component, and apply summation moment at joint G, but we cannot eliminate the horizontal component if we resolve HE at joint E. The reason why I have stated that it is more logical to resolve HE at joint H such that the horizontal component will pass through at point G, our moment center, and it will not create moment at that point. Here is now the horizontal and vertical component of HE. We can now apply summation moment at G, assuming that clockwise moment are positive. So we have HEY, that is the vertical component of HE. The moment arm is 8 meters. That is clockwise with respect to joint G. And for FH, that is counterclockwise with respect to joint G. The moment arm is also equal to 8 meters. So the first term of the equation will be positive and the second term is negative, since that is a counterclockwise moment. From this equation, we can replace the value of HEY, that is equal to 0.781 of HE, the vertical component of HE, and the only unknown now will be HE. We can solve for HE, and that is equal to 40.01 kilonewton. Since it is positive, our assumption that HE is acting away the free body diagram, or that is tension, was correct. So I write here that is tension. We have already obtained member force HE. So the next thing that we are going to do is to obtain for HC by passing cutting plane C, considering the lower portion as our free body diagram. After passing a cutting plane, our mindset is to simplify calculation. That's the reason why we are selecting the free body diagram below or above a cutting plane, to the right or to the left of a cutting plane as our FBD. In our case, and in my own opinion, it is more complicated to use the upper portion of the truss as free body diagram to solve for member force CF. It's the reason why I will select the lower part of the truss, the free body diagram below cutting plane C. Here is now our free body diagram as we pass cutting plane C. We will replace the severed member N with a force, and the direction of those forces are all assumptions. After solving or performing the analysis and it will came out to be positive, then our assumed direction was correct. The next thing that we're going to do here is to find the joint wherein we can apply summation moment to solve for CF as possible as we can, we will select a joint wherein forces will intersect or pass through to eliminate them from the equation. The result will be a simple equation. So if we select joint A as our moment center, we can observe that AD, AB, the vertical reaction at point A, BC, and the horizontal component or horizontal reaction at point C will pass through, and those forces will not create moment. The only forces that will create moment with respect to point A will be CY and CF. Of course, we can also apply summation moment at D, but we cannot eliminate AB, BC, 75 kilonewton at point C. More term of the equation will be involved in the calculation. The reason why we have to select point A so that we can simplify the equation to calculate for the value of C. Assuming that clockwise moment now are positive, we apply summation moment at A is equal to 0. We have CF multiplied by its moment arm, that is 8 meters, that is clockwise with respect to point A, and 78.1, that is the reaction at point C in vertical direction, multiplied by its moment arm, that is 8 meters, that is counterclockwise moment with respect to joint A. From that equation, we can solve for CF, and that is also equal to 78.13 kilonewton. Our assumption that CF is acting toward the free body diagram was correct. That is a compressive force. So I write here that is compression. If we apply summation moment at point C, we can solve for member force AD. Since BC, AB, 75, 78.1, and CF will pass through joint C, the only unknown will be AD. And here's the equation. We apply summation moment at C is equal to 0. Clockwise moment positive. AD multiplied by 8 is clockwise with respect to point C, that is positive. And 78.1, that's the reaction at point A, multiplied by its moment arm, that is also equal to 8 meters, is negative since that is a counterclockwise moment with respect to point C. And from that equation, we can solve for AD, that is equal to 78.13 kilonewton. Our assumption that AD's tension was correct because 78.13 came out to be positive. After solving for member force CF, we will pass another cutting plane in order to solve for member force BF, just like what we did on the upper portion of the truss. Before we can solve for member force HE, we pass cutting plane A-A to solve for member force HF, then we pass cutting plane B-B. We have 3 unknown member forces, thereby we solve for member force HE. That is also what are we going to do in the lower portion of the truss. We solve for CF, then we pass cutting plane D-D. We have left with 3 unknowns, BF, BD, and AD. Since we have 3 equations of static equilibrium, we can solve for those member forces. Here's now our free body diagram. After we pass cutting plane D-D on the truss, we select the lower portion of the truss as our free body diagram because, on my own opinion, it is less complicated to use the lower portion than the upper portion of the truss. Of course, we can also solve for member force AD, BD, BF if we make use of the free body diagram above our cutting plane or the upper portion of the truss as our FBD. Then we will again replace the severed member with forces, and all the directions of those forces are assumptions except for CF. We have already solved for member force CF, and we proved that that is under compression or a compressive force. That's the reason why it is acting toward the free body diagram. Again, we will select a moment center wherein we can solve for member force BF. And for the selection of moment center, we have to consider on how to simplify the calculation. That is, in other words, we have to select a joint wherein some of the member forces will pass through such that those forces will be eliminated in the calculation. It is clear in this free body diagram that if we select now joint D as our moment center to solve for member force FB, we know that BD, AD, and AY will pass through joint D. Those forces will not create moment with respect to joint D, then those forces will be eliminated from the equation. If we select joint A as our moment center, BD will not pass through at joint A. Therefore, it will create moment with respect to point A. In doing so, we are making the calculation more complicated because we will have 2 unknowns, BD and BF, and those member forces are both inclined member forces. So the calculation will be more complicated. We select joint A as our moment center. The reason why we have to select a moment center at every free body diagram, we will select a moment center wherein we can simplify the calculation. The next thing that we're going to do here now is to resolve for member force BF, because we know that that is an inclined member force. So we have to obtain its vertical and horizontal component anywhere to its line of action by applying the principle of transmissibility. We can resolve that at joint B or at joint F, but it's more logical to resolve that at joint F so that the horizontal component of BF will pass through again at moment center at joint D. Thereby, the vertical component will be the force that will create moment with respect to joint D, together with some other forces that will not pass through joint D. So here is now the vertical and horizontal component of member force BF. We will apply summation moment at joint D. We will replace the value of the vertical component of BF with 0.781 BF, that is the vertical component of the members on the upper portion of the truss. Since they have the same inclination, they have the same vertical and horizontal component also. I will now apply summation moment at joint D. AD, BD, and AY will pass through joint D. As we stated earlier, they will not create moment with respect to point D. The only forces that will now create moment will be BF, CX, CY, and CF. So CF multiplied by its moment arm, that is 8 meters, is clockwise with respect to point D. The vertical component of BF multiplied by its moment arm, that is also 8 meters, is clockwise also with respect to point D. CX, that is also clockwise, the moment arm is 5 meters with respect to joint D. And CY, that is 78.13, is counterclockwise with respect to joint D. The moment arm is equal to 8 meters, we equate it to 0. And from this equation, if we replace the value of CF, CX, and CY, we can be able to solve for BF, and that is equal to negative 60.02 kilonewton. Since 60.02 came out to be negative, then our assumed direction was incorrect. It should be tension opposite of what we assume, which is compression, that is acting toward. So it should not act toward, it should act away the free body diagram, because our answer is negative. So as you can observe, CF, BFY, and CY have the same moment arm because they are collinear to each other. So the moment arm is 8 meters with respect to point D. We have already solved for member force HE, BF, and CF. The only unknown now will be member force DE. To solve now this member force DE, we pass a cutting plane that will cut the portion wherein member force DE will be included. Then, by using the upper portion as our free body diagram, we can apply summation forces along X, and the only unknown will be DE, since we have already calculated the value of BF on this truss. Here is now our free body diagram after we pass cutting plane E', the upper portion of the truss is our FBD. We will again replace the severed member with forces. For DG and DE, those are assumptions, but for BF and CF, we have already calculated the value of those member forces. Therefore, we are confident that BF is acting away the free body diagram because that is a tensile force, and for CF, that is acting toward the free body diagram because that is a compressive force. Since we are assuming the direction of member force DE, after solving the problem and DE will came out to be positive, then our assumption that that is under tension was correct. But if it is negative, then our assumption that that is tension was incorrect. It should be opposite of what we assume and should be compression. Since we will apply summation forces along horizontal to the free body diagram, we have to be very careful for the directions of inclined members. So we have to focus our attention to this member force BF. Since that is under tension, the horizontal component should be acting to the left, and for the vertical component should be acting downward. Just like we have labeled here, direction of horizontal and vertical component of member force BF. In doing so, we can avoid errors for the calculation of member forces. If, for example, BF is under compression, therefore, the direction of the horizontal component is to the right, and for the vertical component, that is upward. If BF is compressive, because the direction should be upward to the right and not downward to the left, as we can observe to this free body diagram. We will now apply summation forces along X to our free body diagram. So there are three forces acting on X direction or horizontal direction to our free body diagram, that is 50 kN applied at joint G, member force D and the horizontal component of member force BF. We will apply summation forces along X is equal to 0, right, for forces positive. We know that 50 kN is acting to the right, so that is positive. For DE, that is acting to the left, so that is negative. And the horizontal component of BF, that is BFX, is acting to the left, that is also negative. Since we have already obtained the value of BF into our previous calculation, and that is equal to 60.02, we just multiply it by 0.625 and the result is equal to 37.51 kN. We just substitute to the value of the horizontal component. The only unknown to this equation is member force DE. We can now solve for DE, and that is equal to 12.49 kN. Our assumed direction was correct since 12.49 kN came out to be positive, so I write here that is under tension. I hope you learned a lot to this example. To those who want a copy of this file in PDF, like and subscribe. Comment down your email below and I will send it to you. Thank you.